This is the Amp Hour Podcast, recorded April 28th, 2014. Episode 196, with guest Mike Engelhardt, Spice, Simulator, Synteresis. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Mike Engelhardt from Linear Technology Corporation.
Welcome, Mike. And we are Daveless this week, but we don't need him because we're going to hear all about Linear Tech and LT Spice. And I am, as an analog guy, I cannot state how excited I am to talk to someone in charge of a product that basically did half my job for me. Does half my job for me.
Very cool.
So let's hear a little bit of background. What is your path towards linear technology and where you are today?
Well, I have been writing simulators for a real long time. Actually, I've been writing physical simulators since 1975. And
wow.
LT Spice is actually those were not all circuit simulators. LT Spice is my third circuit simulator. But basically, what happened is, about 16 years ago, I realized that there were numerical methods that you could apply to SPICE programs to make a better SPICE program, make a faster and more robust SPICE program. You know, some of these methods were, basically out there in the field of numerical methods, and some of the methods I had invented myself. So I was pretty sure I could write, the world's fastest SPICE. But, if you come to that point in your life, what do you do with that information, And, do you try to start a company or what do you try to do? Anyway, I'd written enough simulators to know that the best simulators are actually not from software companies. They're not for sale. They the problem is that the amount of money it takes to develop, the best simulator in any particular field of engineering larger than an amount of money that you can recoup with licensing fees. So,
okay.
Yeah, and I actually don't know of a single field of engineering that shows an exception to that. If you want to simulate charged particle optics, how would you electrodes and iron and coils of focus and electron beam? The best simulator for that is not for sale. It was actually developed by a company that designed scanning electron microscopes, and they developed it as a competitive advantage so they could design better microscopes than their competitors.
Is that just because the market would be so small for the people that would need to actually buy that? You'd have to charge $250,000 in order to make that the software company worth it? Is that kind of what you mean?
You'd probably have to charge a lot more than $250,000 for it. You'd probably have to charge more than $1 million for it to recoup your development costs. It takes a few people. It takes a while. And then you have all this risk. You can't develop a project like that just to break even. Right. And you would need a lot more money. Like in the case of scanning electron microscope, in this case of charged particle optics, there's simulators that go for free up to $100,000. The best simulator was designed by a scanning electron microscope company, and they developed it explicitly to be better than any simulator you could buy from any company at any price, so that nobody could design a better microscope than they could. Why they developed it.
Yeah. Well, and that's interesting too, because I've heard stories. I don't know if this fits with what you've seen, but a lot of times that there's internal tools that people are using for developing stuff on their own, right? And that just happens to be, okay, well, we can spin this out, we can use this as a marketing tool as much as we're using it as an internal tool to develop the product itself.
I'd be interested in knowing cases like that, because usually these in-house simulators are not used externally. And I know of lots of examples of Intel has a really good high-speed MOS solver, and they developed it in-house, and that's the fact that they developed their own simulators. Basically, the difference between Intel and AMD. AMD buys their CAD tools like ACES and Anagram, and Intel develops their in-house ones, and the consequences of that strategic decision is ultimately reflected in the quality of their products. But and anyway, every field of engineering you really see this pattern where the best simulators are developed by the people that need them and not by software companies. Even like if you want, say you want to know the radar return from a warplane. Well, you could buy, high frequency 3D, tessellation and mesh programs to try to compute the radar return of structures of different shapes. But, the best simulators for computing the radar return from a warplane is developed by the people that make those planes, and they don't sell the simulator. They sell the planes. That's just the business model. Anyway,
Right.
I knew that, and that's why when I had this information about how to write the world's fastest spice, that's why I didn't try to, join an EDA company. That's why I looked for an IC company that was interested in it. And of all things, Linear Tech on their website had an ad for a position that I could shoehorn my agenda into what they wanted. They wanted something.
Really?
Yes. So I answered an ad on Linear Tech's website, and that's how it started.
So you hear that, folks? You want to develop the next LT Spice, you just got to read the online ad. I don't think that story still holds, Mike. I got to say, I think I think this might be an outlier.
The first time I told that to people, I didn't realize how funny it sounded because a bunch of people were laughing when I said that. But that's literally what happened. I will admit that the position that they wanted was different. It was just a compatible agenda. You know what I mean?
Right.
But I wrote LTICE explicitly to be the world's fastest spice. There were all sorts of numerical methods that I put into it, like node reduction and new ways of integrating differential equations. Just a lot of things are into it. It even does self-authoring code.
Oh, what does that mean?
Well, the first version of LT Spice didn't do this, but in 2008 I made it self-authoring, and that means that when you push the little running man icon, and the schematic capture program produces a net list, and the simulator parses the net list and parses it into stores it all in data structures. Once that happens, then LT Spice looks at all those addresses and those data structures, and it actually authors an assembly language program to solve that particular circuit. It writes a macro assembler. Yes, and then it assembles it, and then it links it, then it calls that address as a function, and that's the way it works.
And that's why it's so fast? Is that the idea?
That speeds things up. Yes, It makes it a factor of 3 faster. And I'll tell you why it's like the thing is that when you're writing in a high-level language, because all operating systems today use dynamic memory allocation, you don't really get the, you have some data X and you refer to that X in your program. Well, you're not referring to the data X and you're not referring to the address of the data X. You're really referring to the address of the data X. And once the program runs, it'll allocate some memory and it'll be, when you know where it's going to be stored, but you don't know what the address that is. And then once you get done with all that indirection, it takes a long time. In fact, it takes longer to get your memory into the math floating point unit than to actually do the math. That's the problem. Right. Now, that's not always the case. The reason why it takes longer to get the stuff into the floating point unit than to doing the floating point math is because of the specific operations you're doing in SPICE. You probably know that SPICE is doing successive linear approximations to a nonlinear system, which means it sets up the system simultaneous linear equations and solves them. Basically, what it's doing is it's solving matrices.
Yeah. All the stuff that I hated doing in school.
Exactly. Exactly.
Yeah, it's never ever doing the Laplace transforms directly. It's always doing it by little guesses, little changes, little guesses, little changes, right?
Yeah. Well, Laplace would be a linear thing, but when it's solving your diodes and your transistors, all those nonlinear elements, it's expanding the underlying nonlinear system as a Taylor series, keeping the first two terms, and then it's finding the Taylor series that actually approximates the system really well, and that's what it's doing. Anyways, in doing that, it has to solve a bunch of matrices, and when you solve a matrix, you're mostly doing addition, subtraction, and multiplication. There's a few divisions, but there's only one division per unknown. Division takes a long time, but addition, subtraction, multiplication, those can occur in only 3 volts, or 900 picoseconds. right?
Which is fast.
Yeah, it's fast. Yeah, you can
That is quite fast.
Yeah, you can multiply two floating point double precision 64-bit numbers to a 64-bit accurate result in 900 picoseconds. That's what your home computer does.
Right, all without an accelerator or any fancy like FPGA type hardware or like custom hardware. It's all
no,
just
the custom hardware
right
will be
there.
slower, but it'll have more of them.
Right. Oh, right.
Yeah. So if you can parallel process it, you would get a net advantage. But no, the floating point units is part of the Intel hardware now, and it can do those three particular flops in 900 picoseconds. But you never get that performance from anything that you write at application code compile time, because when you're writing the program, you don't know what the address is going to be, because you're dynamically allocating memory. Even if you're writing an assembly language, but if you've already called malloc, you know those addresses. You can write some code with those addresses in line, and you can run the pipeline hot, and that's what I do.
Mike, I have to say that my excitement at the beginning of this interview, thinking, oh, we're going to talk circuits and everything else, is quickly being replaced by fear as we talk about programming stuff that I usually run from, like a sprinter.
I hate to disappoint you on this.
No, it's okay. It's good.
I'm actually not trying to impress you.
This is like your life, though, right? This is what you do. I mean, you mean to optimize. I get it. I mean, it's an engineering problem.
Sure. Obviously, you have to be pretty motivated to want to do that. Nobody does that, okay? But, honestly, the hard part of this is convincing people that it's difficult, right? I mean, there's only 4 opcodes: add, subtract, multiply, and divide. How hard can it be, right? I mean...
Well, I mean, it's all of computing, I suppose, but
yeah,
it's just bits, right? It's just code.
Yeah, why do you think they call it code, huh?
Yeah. So, is it hard? It is difficult to convince people that this is a tough problem to solve, or is it just that people think, oh, well, it's already been solved?
If life were fair, the hard part would be convincing people that it's hard. But life is not fair. If you tell people you're doing self-authoring code, and you tell them why, and you get into this blind, and you tell people you're going to pipeline hot, and you tell people why you can't keep the pipeline full with any code that you write at application circuit compile time, they'll have one of two different reactions. They'll either get blurry-eyed and, politely sit through that part of the conversation until they get to a part of the conversation they're more comfortable with, or they'll say, you can't possibly be doing that because it's too difficult,
You've given some seminars before, haven't you? There's always that guy in the back. He's like, well, wait a second. I've written assembly. So what is pipeline hot? I'm sorry, You might have to explain more to me, but hopefully this also translates to listeners.
The math coprocessor has this pipeline. Okay. Normally the pipeline is empty. Okay, it's there's nothing in it because it takes so long to clock the data from memory. You have to take the address of data. And usually you're indexing off of the address of the data. You index off that, and you get the data, and you clock that into your floating point unit. Once all that happens, that takes a lot more than 3 clock cycles.
Okay.
All right.
Okay.
And the pipeline is empty. But if you do self-authoring code, then you're actually doing code with these final addresses inline in the object code. Okay, now the data is not, because you reuse this code many times. When I write this program, I may never have to rewrite it for the whole time that the simulation is running. I'll just keep using the same code over and over again. So the variables themselves change. The data is not in line, but the address of the data is actually in line instead of the address of the data. And in fact, it's actually some if the high level equivalent code, the high level C code would be indexed off of the address of the address. But anyway, if I do that, then the pipeline is full, and as a sloppy manner of speaking, I just say I'm running the pipeline hot instead of empty.
Okay. So you're removing overhead. That's basically what you're saying, right? I mean, all of those things that computers abstract out because you don't want to have to do hard code this necessarily on other programs where you're more interested in other things, right? You're trying to get this efficiency so that you do it up front.
Yeah, it is basically removing overhead, and it when basically every time the floating point unit gets a clock, it actually does something instead of simply getting the data the next step along in the pipeline.
I get you. Yeah, that's
so you
crazy.
have a pipeline. So you're loading data while you're executing other instructions. But if you are only doing addition, subtraction, multiplication, then getting the data to the executor, the thing that executes it, takes a lot longer than the actual execution.
Huh.
And the pipeline is empty. So you do clocks that don't actually, you spend a lot of clock cycles in your floating point unit where no instructions are executed. You simply sequence the data the next step along the pipeline.
Huh. That's so. Why don't more people do this then? I mean, maybe they do, and I just don't know that. But why don't we hear about other people doing this?
I think that it's perceived as something that's pretty difficult. There's very little code that does this. In academic stuff, I've had various mentors in writing LT Spice, and one of my mentors mentioned to me maybe 20 years ago that there was a thing in academia that the fastest way of plotting the data would be to write a program to plot it, and then just execute the programming the data and plotting it. And that was of academic interest, and no one actually implemented it. But it always stuck in my ear as something interesting. And I found a good use for that sort of thing.
Okay.
It is a little tricky. There's, and it's not, it's ambitious. Okay. I like to joke about, I like to, say that the hard part is convincing people that it's difficult, but, there's a lot of software technician work to it. I mean, just getting an address that you execute is going to take you an afternoon.
Yeah. Oh yeah.
You can't you can't call malloc and call it as an address. That's a bus error. Your program will crash if you do that.
I'm so out of my element right now, but I'm trying to hold on, Mike. I'm telling you, I'm trying to hang on.
All right. Okay.
So,
here's the deal.
So
here's the you know the address called malloc, or the function called malloc?
Yeah, right.
Okay, great.
Memory allocation.
Okay, now
right?
memory allocation. You allocate some memory, and you can write to it, and you can read to it. However, if you cast that address as a function and then call it, the operating system will say, no, that's not a function. That's data. You must be making a mistake.
Oh.
I'm going to stop this program because it's either a mistake or it's a virus. Some virus is doing that. Okay.
Right.
And so Unix has basically always had this kind of protected memory thing where some data would be classed as code and some as data. And it would be okay to execute code, but it's not okay to execute data because it can't be correct. And then since Windows Vista on the PC on the Intel platform, I forget which Pentium chip, they eventually had hardware support of that you could set up addresses as data or code so that with minor extensions to the operating system, you could make give hardware support to making sure that you never executed data. Because if you execute data, it has to be incorrect, and you should just stop and say this program has a bug at it instead of executing whatever was in that data, because that would have to be wrong.
Yeah.
So you can't just normally you can't just call malloc. Well, you cannot call malloc, poke a bunch of bytes into it and call, even if it's perfectly valid, and call it before it executes the first code. It says no, that those addresses are not code, it's data. And so you can't execute it. So you have to go into every operating system and find out what means exists for calling so that you can execute something, code that you basically already, that you're assembling yourself, that you're assembling and linking yourself on the fly. Well, then it's different in every operating system. Mac OS has one way of doing it. Windows has another way of doing it.
Okay. Yeah. So that was going to bring me to my next question, which was, do you kind of curse the sky every time Windows is like, we have a new release, or Mac now that you've released for Mac, is it the same kind of thing? It's like, crud, new software.
It's just too popular to dislike Windows. I just deal with whatever it does. I don't really get personally involved in it.
Right, but you get to dislike OS X now too. I just mean like every time there's how often do you does it? But is it like every time there's a software update that kind of, because it's like it seems to me like you're running kind of close to the metal, right? As close as people do on CPUs, right? And so does that
sure? I mean,
end up affecting?
what I do is I look at that I look at that CPU, I look at the input data, I look at the output bit pattern I want, I figure out what's the least amount, what instructions can I execute to pump the least amount of charge through that CPU to get that final bit pattern. I mean, that's the problem.
I like that. You should market the software as well as being energy efficient. No wasted cycles.
It is.
Yeah.
It's funny. After I was like in year 2 or 3 at Linear, Robert Dobkin pulled me into his office and he asked me about this thing. He heard about all these things. What's the advantage of this? And I says, when you run it, if you hook up an amp meter to the power cord, it will draw less power.
Right, and that spoke his language, right?
No, he didn't quite know what value that was because he didn't care how much power the computer drew.
Does that sell more chips? We have not yet had Bob on the show. That's a long-term goal of ours. So we'll be sure to remind him of that story when he finally
he won't remember.
Capitulates.
It's okay.
Yeah.
That was like 14 years ago.
Wow, so 14 years ago. So what was the landscape like before that then? I mean, so you've been in the software game and the simulator game a long time, but I'm guessing you had a cognizance of what it was like before that. Was it mostly people paying gobs of money for off-the-shelf tools?
It was at Linear, yeah. Before I was here, they did not use their own, they didn't have an in-house splice program.
Okay. And so I guess I think about it from the user side as well.
And I don't think every analog, huh?
I was thinking from the user, so like from the I'm thinking about number one here, right? So like, LT Splice is a really good service to all of the users of components from LT, right? And and so I was thinking on that side of things as well.
I'm sorry, I don't understand the question.
So kind of what was before you showed up at Linear Tech and started working on LT Spice and, it was released into the world as this free product that people used, kind of what was the world like before that then? I mean, was it mostly people going and paying a bunch of money for a P Spice or an H Spice or a Top Spice or something like that? Was there any other similar type of solution out there in the marketplace?
I don't know if there was a free Spice. There were some low costs. I tend to use, I had my own. I would actually just compile the source code of a Berkeley Spice. But, the source code to Berkeley Spice has a lot of problems to it.
What kind of stuff?
First of all, it doesn't solve for very many devices. Part of the SPICE program is that it has the IV curves of all these semiconductors in it.
Right.
But the problem is that Berkeley Spice can't actually execute the IV curves of any commercial semiconductor. It doesn't have like even a diode. There's if you get a diode model from a semiconductor manufacturer, it actually will not run in Berkeley Spice.
Huh.
It just doesn't. Maybe it uses a recombination charge model. It won't a recombination current model, and it won't handle that. H Spice has other ways of making the IV curve non-purely exponential. So it has deviations from exponential IV curve. I mean, above and beyond a series impedance of resistance. There's intrinsic, nonlinear power. It's not actually exponential, and Berkeley Spice won't handle anything that's not exponential. So there's that, and that's just a diode. The transistors, you won't be able to execute transistors at all. There's other problems is that, because SPICE is doing successive linear approximations to the nonlinear system, you need to have the IV curves be continuous in value and slope. That is, they need to have a continuous value, continuous first derivative. And if they don't, it's very hard to iterate to the exact point on this curvy line if it's not a smooth curve with a continuous first derivative. And every semiconductor in Berkeley Spice has a bug in it one place or another. The curves are not continuous in value and slope. And a lot of those bugs are actually in commercial Spice programs.
Just because it got copied over, or what?
Because they got copied over. P Spice has that. P Spice has discontinuities in the even the diode IV curve.
Really? So what would happen? So I guess that's kind of interesting to me because I mean I always think about spice at a very high level, and I'm guessing you're like staring at the atoms of the universe, where I'm kind of looking at a forest, right? So what would happen? So I put a diode in a P spice, or someone using the original model, and it would be like. Would it just be that if I hit that very particular operating point, the whole thing would blow up, or
it would the discontinuity left in PSpice from the academic code is pretty small. You would have to say, I want an extremely tight relative tolerance. I want to solve this thing, I want to solve the point on the IV curve to like 10 to the minus 10 or something. I'm certain that would cause problems if you try to hit this discontinuity. The discontinuity is something like a few parts per million, I think.
Oh, okay.
I haven't looked at it in a long time ago.
Okay,
but
so
it's there in every device. But anyway, yeah, every IV curve in Berkeley Spice has discontinuities in it. None of them are correct.
So what kind of crossover then? So like if we took LT Spice at a very high level and compared that to Berkeley Spice, how much effective crossover is there? I mean, like how similar does it look?
What is similar is that they both use a global Jacobian. And by that, I mean, you know what a derivative is? Okay, if you have a multidimensional derivative, that's called the Jacobian matrix. Okay. And the intrinsic part of the thing that makes a spice program to me is that they use a global Jacobian. The whole circuit is solved in one huge matrix. That's the most accurate way of solving a circuit. And both Berkeley Spice and LT Spice use a global Jacobian. And they both use implicit integration of the differential equations. Their syntax is mostly, I would say their syntax is essentially 100% compatible, but the implementation is different. I use a different parser and such. I think that's mostly for performance reasons. I started using the Berkeley parser, but it was just really slow. It couldn't expand subcircuits very fast. Huh. You couldn't design an IC because you'd spend 10 minutes expanding all the subcircuits, instancing all the thing out to netlist. Actually, let me give you a little bit more detailed answer, because people always, I'm kind of in a rant mode here because so many people think
well, that's good for the amp hour.
Yeah. See, people often think that the only difference between one SPICE program and another is the user interface and not so much the SPICE program. In Berkeley SPICE, in LT SPICE, that's actually not true at all. And it can be quantified from a source line count point of view. If you download Berkeley SPICE, you get about 200,000 lines of code of stuff. Okay, if you just word count every file you get.
Right. Yep.
Most of it is actually dead code. If you delete a line of code from Berkeley SPICE and recompile, you'll have exactly the same object code. Most of it is dead code.
Huh.
And once you get rid of all of the dead code, and then use forget the line wraps. Okay, don't line wrap it to 80 columns, but just use natural line lengths for the whole thing. You end up with about 85,000 lines of code of stuff. Okay.
Yep.
Now LT SPICE is not 85,000 lines of code of stuff. It's a little over 500,000 lines of code. So right there, you say, okay, you can't really say that LT SPICE and Berkeley SPICE are particularly similar because LT SPICE is 6 times larger or whatever. But also, every single line of code, those 85,000 lines of codes, they've all been re-implemented or corrected for bugs.
Oh, because so there's like a lot of hot fixes and patches and stuff like that.
Well, it's like every Berkeley SPICE semiconductor has discontinuities in value or slope, so all of those have been removed. Another aspect to the to making a SPICE program is you need to know the differential behavior. You have to compute this multidimensional derivative thing I call the Jacobian. Berkeley SPICE has bugs; they don't get every Jacobian element correct, so you have to figure out systematic ways finding these errors in the Jacobian and getting those. And then there's other problems. Some of the things in Berkeley SPICE are machine generated derivatives. with like symbolic math programs, and those things won't catch singularities that you have to like work around, say, applying L'Hopital's rule to, because you may have an expression which is physically correct but numerically singular, and you have to use some other mathematical method to get a non-singular, to remove the convergence error that you would get if you were to use that. So there's not very much. So Berkeley Spice and LT Spice have very little in common as far as the implementation of the code itself. It's precious little.
Okay, so it's mostly name. It's still Spice, right?
Yeah, they are. Yeah, and for me, Spice is anything that uses a global Jacobian.
Okay, that's a really unique and interesting way of classifying it. Actually, I wouldn't have ever come up with that. I would think something that helps me solve circuits. I guess that's kind of abstracted from me. And I guess it depends on the level of usage as well, right? I mean, if it's a student, using it to get around their homework where they should be calculating a voltage divider, that's a lot different than someone who's doing, deep simulation of physical parameters and, actually trying to model physical circuits, right?
I appreciate that.
So what about that? I mean, what about that span of usage, right? So I'm guessing the people, the chip designers at LT are using this in some capacity in I don't know if it's the applications group or the design groups.
LT Spice is used in-house for IC design. It's used as I wrote it to be the world's fastest spice. That's why I wrote it because if you had this thing, you could design better analog circuits than if you didn't have this thing. So it's used in-house for IC design, and it's exactly the same executable that you use. It's not crippled in any way. It doesn't look at your IP address or whatever. It's not crippled by, node count or, it's not crippled by circuit content either. You don't have to have a linear tech part in it, and you're okay to use third-party models in it. We're okay if you as a non-linear tech employee or customer or whatever use LT Spice for something other than trying to sell an LT Spice part to yourself. That's we're totally down with that. We're just going to be the analog company with the world's best spice, and we're going to let people use it.
Oh, and actually, so that's actually a really good, interesting point as well with the the chip designers use it, because I think about, again, that scale and that kind of dynamic range of usage cases, right? I mean, me as just a casual user, even an intermediate user, is a lot different than someone designing the chips as well. But I think in those extreme cases, that time speed up that you're allowing for that much faster, that allows for more iterations on the actual design cycle of the chips themselves, which could take large amounts of processing cycles that normally outside users might not have or experience that often.
It's a real big deal for in-house design because the typical linear tech part has between 5,000 and 8,000 transistors in it. To simulate, if it's we have about slightly more than the majority of our business is switchboard power supply components. So to simulate, the first 5 milliseconds of a startup transient analysis, it could take 30 hours on something like PSpice, but I can compute it in 6 hours, and the guy can get the result, process it while he's still aware of why he thought that simulation would be useful to himself. And make and iterate something in it, and come back in the morning and look at something new.
Yeah. And so, I'm not sure how much you're allowed to say with this, but is it is it using like a server model where it's thrown to a centralized processing at Linear Tech, or is it just everybody on their PCs and doing it there?
Everyone uses it on their own local PCs. The server model I just don't understand for numerical methods. I mean, a server isn't any faster than your home computer, so why would you try to put everybody's computation on the same server?
Oh, so wouldn't want to use queuing because you'd want to be able to basically distribute the workload over lots of.
About once every year or two, I go get the Extreme Edition i7, and I get the best ASUS motherboard I can. Uh-huh. I get a water-cooled thing. I get some G-Skill RAM. I build this thing. I benchmark it, and then I say, okay, here's your recipe. Give every IC designer this water-cooled Extreme Edition IC thing like that, and that's what they use.
Oh, that's awesome.
And they do it locally. So yeah, I haven't done that in a few years though. I'm interested in. I did it the last time I revved it was about 2 years ago. And with the X79, I'm kind of wondering if they're going to get something new about the X79 chipset.
Yeah, I guess you're probably staring at the data sheet, huh, for the Intel processors and everything as well. You're probably, because you're doing all that lower level stuff, that you really want to see the specs on that thing.
I look at the assembly manuals for them, but ultimately you just have to benchmark it because you can. An unhasted hypothesis in numerical methods is really worthless. It's just you have to build the hardware and measure how fast it runs, and that has to be that's what guides what algorithms I try. I try different algorithms. I have to try it on a hardware. I mean, I can have ideas about which would run faster or slower, but these things are so complicated. There's been a number of times I've been strongly surprised with what Intel made and the performance of their machines.
So this is like a beautiful piece of irony. Like the guy that makes a great simulation engine says, don't just simulate it, folks. Make sure you try it in the real world as well. That's a beautiful statement.
I'll tell you. No, but they're actually related to different. That's true too. But there's what I'm actually referring to is a different issue. One time I was really surprised with Intel hardware when I was making LT Spice multi-threaded, which is also in the year 2008.
Oh yeah, yep.
In the middle of that project. They had, there were quad-core processors out there, and that was when the i7 was announced. It was sort of I was just making LT Spice. I'd made it released it for a couple of months, and then the i7 was out there. It was 4 threads, and it was hyper-threaded. And I says, oh, crap, it's hyper-threaded. I'm going to have to write an algorithm, find out how many floating point processors are physically there, and then limit the threads to the number of floating point processors, or the thing is going to run slower.
Oh, right, right. Because you're trying to divvy up tasks over the virtual processors.
I thought they'd hatch it. Because I remember when multi-threaded came out, it didn't work very fast. It wasn't exactly exciting. Right. So I built up an i7. I tried it all. I wrote this algorithm, and I was dumbfounded by the fact that the multi-threaded, or the hyper-threaded quad-core was indistinguishable from having 8 cores. You could not tell the difference with software.
Interesting.
And I had to think a long time about this. Oh, yeah. Hyper-threading means having 2 decoders, and for the instruction set I'm using, it actually takes longer to decode the instruction than execute it. It only has to take a picosecond longer, but if it takes longer to decode than execute, if you have decoders, you can't distinguish that from having 2 cores.
Huh. That's interesting.
Because think about 2 are decoding, and it says, okay, I need the core, and they say they both need the core at the same time. Well, you wait, one decoder gets the core, and then 300 picoseconds later, the other one gets the core and executes its instructions, and both cores are running full tilt, and the cores are running at full tilt. As long as it takes longer to decode than execute, you can't tell the performance difference from having 2 physical cores. Huh. I mean, it's okay. Yes, the 2 threads. One thread was delayed by 300 picoseconds, but you're never going to be able to measure that, right. Not from outside of the die.
Right.
So that was a big surprise. I mean, I assumed I was going to have to write an algorithm for detecting how many cores were there and limit my threads to the number of cores. Well, it wasn't true.
So again, the multi-threading, the decision behind that was just, again, another optimization to try and up the speed for your chip designers effectively?
Yeah, it's more of use for chip designer than for board level work. I mean, it has some use in board level work, yeah. But for chip design, if it's some BiCMOS design with 4,000 BSIM4 devices, and then the simulation speeds improves somewhat linearly with the number of cores you have, at least up to the 12 cores that I've tried it in.
Huh. So could you tell us a little bit more about that chip design side of things? So I have a model open. I have the if people want to follow along at home, I have LT Spice 4 open right now, and it is up to date. And I am the the LM741 model open, right? That's one of the example models. I have that open, and I'm looking at the model.
Which one did you say?
The LM741.
741. Yes, it's the examples educational.
Yep, exactly.
Okay, sure.
Oh yeah, sorry, it's
let's.
Yeah. So this is how, this is basically a pretty good approximation of how chip designers would actually be doing it, right? And they have discrete transistors with modeled parameters and all that other stuff. And I've always been really interested in the construction of the models themselves and all of the parameters that are actually inside of that, of the model parameters basically for each transistor. And I know that these match against physical characteristics, but I was wondering if you can give us like a higher level overview of if someone wanted to try and read this, human readable, try and read this to say, oh, well, this transistor will do this, and like, oh, this, the BF value goes up a little bit. What will be the output effectively for the model?
Okay, in that 741 example, you'll find the model statements written at the bottom of the schematic. It says the model for the NP beta of 125, and it has some capacitances and has some base resistance. And then the lateral PNP has a lower beta and different capacitances and a different RB. That is actually not a particularly good model for those
right.
Things. That's just something I made to the oldest guy in the building who designed op amps and said what would be about the beta capacitances and the RB. So I would make something that works like a 741. But those models are not good enough for IC design.
Oh, okay.
You could, if you were to, hork up this design, you could, optimize the design, but then you'd find silicon didn't work better because your model wasn't that accurate. The process of making a model is for these bipolar transistors. It's a field in and of itself, and we have actually a different group than my group that does that. They make test structures and they spend time in the lab and they microprobe these things. They look at IV curves and ring oscillators, and they extract the DC and AC characteristics of these things, small signal, large signal, and they alter these models, and that's what IC designers use.
Okay.
If you wanted to know about semiconductor modeling, there's a book you need. And it's called Semiconductor Device Modeling with SPICE. It's written by Principi Mario and Paolo Annotigatti, two Italians, though the English is of native English quality.
Okay.
You need the second edition of that book, and you need to read it. You need to read it cover to cover, and that would be what you would basically need. Okay, once you read this book cover to cover, you would be able to make diode and bipolar models. You might get some luck with JFETs.
Okay, right.
Okay. Now to make MOSFETs, they keep changing things. They keep changing the equations used to model them. So there's other references you need beyond that. But that's your prerequisite there. You'd have to do that, read that book, and decide what else you want to study. And at that point, you need to decide whether or not you really want to do it for a living. It's a fine living. They got fiendishly smart people making these models.
Yeah.
If that's what you want to do for a living. Right.
Yeah, I guess I didn't take a close enough look at the actual model that was down there. I was thinking more on the because I guess the thing that I've always run into has been trying. So I'll be going down a list, right, and I'll have a transistor that I'm using on a board. More likely, I was finding transistors that I hadn't designed in, and it'd be like, okay, well, I want to try and model what's going on here and see what happens. Basically, trying to match behavior against a known new model, right? So if I'm replacing a part or something like that, and what I would do is I would go in and I'd say, I'd right click on a part and I'd say pick a new transistor, and then I'd scroll to the right and I'd see the SPICE model there. And then I'd see all of these different parameters. And then I'd think, well, I can probably try and do this from the data sheet, right? Trying to create something from a data sheet. And it seems like that is incorrect assumption that mortal could do that.
It's real hard to make a model from the data sheet itself.
Huh.
And you have to assume a lot of characteristics of that device. You have to bring a lot of characteristics to the data sheet. So, then you're basically basically making a model from a data sheet is essentially impossible.
Oh, okay.
And it depends on the nature of the transistor. For the bipolars, there's no way, because you have this whole quasi-saturation region that'll never be documented very well in the data sheet. It's basically impossible. For the MOSFETs, you can make a model for a MOSFET that's good enough for switch-mode power supplies. In fact, it's probably good enough for everything, but particularly switch-mode power supplies, it's certainly good enough. But the process is fairly laborious. What I do is I make little test fixtures that will curve trace or duplicate curves in the data sheet. I'll do one to output characteristics, one will be RDS on for different gate voltages, then there'll be gate charge, and then I'll keep twiddling the model parameters to duplicate these curves in the data sheet. Huh. However, the problem you'll often run, and it's a laborious thing that'll take, if you like the best in the world, you might be able to get it done in 45 minutes.
Yeah.
Okay.
You got to want it, right?
Okay. you got to want it.
Yeah.
So, and then there's another problem that you run into, and that is that there often is no transistor that behaves like the data sheet. There's no transistor that exists, and that's because they use different transistors for extracting different curves. So like if you look at the gate charge characteristics, it shows the amount of charge you have to put in the gate to charge up the gate while it's switching. Well, they might have used a particular MOSFET with a different threshold voltage than they used for getting output characteristics. There's no way you can match both curves.
Right.
So you're basically hedging. You're basically hedging ignorance at that point. Trying to make a model. You have to guess what you think they did and didn't screw up, or what you think was the most likely behavior characteristics of the MOSFET. But that's not a concern, because there's so many MOSFET models in LT-Spice. You might find an appropriate MOSFET to use, and if there's not, you can sort. When you open up a MOSFET in LT-Spice and right-click on it, you can sort by different headings. You can sort them. We recommend sorting them first by the gate charge and then by the RDS on, and then find a MOSFET with the same RDS on and the same gate charge and simulate with that guy, and then use whichever source you're interested in for a supplier.
Right, and you'll get pretty close with that, you're saying?
You're probably going to be good enough for that. Now, and there's some MOSFET vendors that if the model isn't there, you can contact the MOSFET vendor and have that, and they will make you an LT-Spice model. Some vendors have taken over the responsibility of their modeling their MOSFETs, notably International Rectifier, Infineon, and just NXP. NXP just sent me some models about a week ago that I included in the distribution.
Well,
so those three
nice.
Vendors.
Yeah.
Yeah, that's nice of them, huh?
So is that something that they would have to do that same? So they'd have to buy that book, Semiconductor Device. I mean, they're doing all this stuff anyways, though, right? They're characterizing their parts.
Oh, the people that and anyone that's in semiconductor device modeling has that book and has read it.
Yeah.
Okay, so NXP has that book. I mean, the people that do it, I'm certain they've read the book.
Yeah, but I guess my real question is then why would some vendors not give a model? Is it just a convenience thing, a time thing, money?
Well, you have to understand that when you're making a power MOSFET, what you want to do is you want to make a MOSFET that's as wide as possible and as narrow as possible, so that for the same gate source voltage, you get a larger change in drain source current. A job, okay? Mm-hmm. And you don't want it to break down. So they might use very smart engineering methods. They might use all sorts of 3D finite element programs to do all of that, okay? Mm-hmm. They can have infinitely smart people doing that. That's what they want to do. They want to make it as wide as possible and as narrow as possible. Now, making a SPICE model for that is not part of that process. SPICE is not part of power MOSFET design. There's no reason why somebody who knows how to make the best power MOSFET in the world would know how to make a SPICE model.
Interesting. Oh.
There's just an unrelated skill. So to be mad at somebody who makes the best MOSFET in the world and not have SPICE models, well, it's an unrelated thing.
Really? So
yeah.
So that narrow and wide thing that the designers are trying to do, is that more of a is that a trial, not a trial and error, but is that a optimization process more than anything else? It's not necessarily.
Well, basically, I mean, the practical dimensions of a power MOSFET channel is a 0.5 micron long and 10 meters wide. That's
okay.
I mean, if you put a MOSFET in your circuit, it's about 10 meters wide. I mean, maybe it's an older one, like 5 meters wide. But it's this very wide channel folded into this little tiny package. And
you're serious? Yeah, sorry. I'm like thinking 5 meters. You're talking about because like trenching and stuff like that, right? Yeah. I was very confused for a second.
It's a tiny structure. You could put 6 of them inside of a TO220 package and rattle around.
Yeah. Okay.
Yeah.
Right.
And there's all sorts of smarts that goes into making a power MOSFET.
Right.
In history, there's a time where they knew how to make. They forgot. They lost the recipe. They weren't for sale anymore. I mean, there's a lot of smarts that goes into that. But SPICE is not part of any aspect of power MOSFET design.
Interesting. That is really, especially because that's such a big part of LT's business with modeling the switcher side of things, which utilize these power MOSFETs, right?
Yeah. I mean, it was we actually developed our own charge model for power MOSFETs because the gate drain capacitance of power MOSFET depends on whether it's on or off. Normally, in a normal lateral MOSFET, like you can print on an IC, the gate and drain, the polysilicon of the gate and the drain metallization are side by side, and whether the transistor's on or off doesn't really change the capacitance between the two. Because the channel's underneath the gate. I mean, it changes the fringe field a little bit. But in a power transistor, the channel is in between the gate and the drain. So whether it's conducting or not moves the distance between the gate and drain. And you have a different capacitance between the gate and drain, depending on whether it's on or off. And since that's the Miller capacitance, and it's the quantity that determines the switching characteristics of the transistor, if you don't have that modeled, you don't have a device that behaves like a power MOSFET at all.
Right.
So that's why at Linear we actually have our own MOSFET device. We did that by looking at, we looked at simulation, and we looked at the bench. We said, why don't these waveforms on bench look anything like the things we simulate? We found, SPICE was about IC design, and you can't print a power transistor on an IC. These power transistors don't behave like monolithic transistors because they have a different charge model. So we, found out why they have a different charge model, and we implemented this VD-MOS thing, and LT SPICE has a charge model that behaves like a power MOSFET.
Wow. So I should mention for our listening audience as well, which is very wide, very varied. I mean, a very wide variety of people listening. If what Mike is saying here does not necessarily make sense to you, there are lots and lots and lots of good books out there for learning about the semiconductor character. I mean, this is basically Semiconductors 101, right? But it's for I think people that are doing board level stuff and just hoping that it plugs in and works at some point, that you have to dig in a little bit more, and it can be a little scary, but it's very, very interesting, I think.
Yeah, sorry if I got carried away.
No, it's okay.
Just got in the excitement of all, I just got carried away. Sorry about that.
That's perfect. And honestly, and that's what it's about. It's about you need to get that exposure beforehand. I mean, I never had any of that exposure beforehand. I didn't even know what I was getting into, and then but it's good to learn about that because I think it's very interesting and understanding. I think from that super low level stuff up to the high level stuff. It seems like you understand all of it. That's what you need to do at a certain point. You need to have some knowledge of every bit of it in order to understand these corner effects and all the weird stuff that can happen in your circuits. I did want to ask about you brought up before the difficulties with simulating switchers and power circuits and stuff like that. Could you kind of expand on that a little bit more in terms of what the difficulty is with that?
Well, I don't know that I don't remember seeing it was the power transistors are hard because generic SPICE programs don't have a circuit element that behaves like a power transistor.
Oh.
But LT SPICE has fixed that, so that's probably the main thing. The difficult thing about power supply simulation is you usually don't have useful models for the controller ICs. And that's actually a big part of LT SPICE. We have this way of modeling switch mode power supply controllers and regulators. that's just a field that I've pioneered.
Yeah, definitely. Yeah, and that's the kind where it's usually those are macro models as well, right? You can't necessarily dig down into.
They are macro models, yes.
Yeah. So are those are like encoded, like basically, is that the compiled function you were talking about before, where it's already optimized and everything?
Well, it's a different type of compiling. When I was talking about compiling before, I was talking about self-authoring, and that's just a software technician thing that deals with getting the math to the floating point processor fast. Okay, the macro models are written with a combination of techniques, and honestly, we just implement whatever is necessary to model the controller.
Oh, okay.
It's necessary. Okay, so we just do what's ever necessary. We to keep our job. So we just do what is ever necessary to model any controller that linear models. Now, for most of it, some of it consists of new circuit elements that have behavior that helps encapsulate the behavior of switch mode power supply. And that's so those things are reused from product to product model. We also have sort of primitive hardware description languages that we kind of write a little program in this kind of ugly language that LT-Spice can parse, compile, and execute. But by compiling there, I don't mean compiling to object code. I mean compiling the data structures that can be executed more like a standard hardware description language like Verilog or VHDL. But it's a very different version of that language. It's a language that we don't make publicly available, and we're not doing that out of some mean-spiritedness. We're doing it because it's a really ugly language, and we just implemented whatever was necessary to model that particular product.
Interesting. So is that still looking at like the transistor level, or is it more behavioral level where it's like
that is all behavioral.
Okay, so it's like it should ramp here, so it gets this input and the output should start to ramp and yank on this transistor gate and that kind of idea.
Yeah, it's like it's some of it is simple things like a voltage control. We have this like a voltage controlled varistor, which means it's a varistor that will break down with a programmable external voltage. So we use those sort of like as emitter followers for the old-fashioned. In current mode controllers, you used to have a soft start that would ramp that would clamp the compensation node voltage during soft start. That method really isn't used very much anymore. And the only thing that soft start does is make the power supply more polite to the rest of the system, so it doesn't draw too much current during startup. For the more modern way of doing soft start is to actually just ramp the reference voltage, so the output is a nice linear ramp up to the voltage that you want. Because that's what a lot of loads like. A lot of the loads are specified to have their supplies ramped in a certain way. You have some PGA and they need the voltages scheduled up. Well, this thing will just paint those waveforms on your load and go from there.
And that's actually how it's physically implemented as well as in this modeling language as well?
Yeah, the model will act like the part. I mean, that's, we want to keep our job, right? I mean,
yes.
it's gotta happen. So.
Yeah, right. Right, it's great. I mean,
we've had some parts that were so complicated we couldn't do that. We had to do a mixed mode simulation. We actually wrote a digital simulator to solve for what the part does. There's a couple of parts. Like the 3780 was just such a complicated part. I actually wrote a digital simulator, a dedicated digital simulator that runs in parallel to LT-Spice. And that's the way we modeled that.
What does the 3780 do? I'm sorry, I don't.
It controls 4 switches, and the way it works is so it controls 4 Mosfets. It will switch from buck mode to boost mode. It's current mode. If you have a buck boost mode controller, it's not too hard to do is voltage mode, because you can just dither all the waveforms and get a linear relation between compensation node voltage and output voltage, and duty cycle. But if you want a current mode, buck boost mode regulator. Boost, I mean something that switches from buck mode or boost mode, so the output can be above or below the input voltage and stay reading a switch mode regulator throughout that. Then you have to switch topologies dynamically while it's while it's running. And way the 3780 does is it does a switching cycle. And then at the end of every switching cycle, it does a forensic analysis of how that switching cycle went. And then it decides whether the next next switch cycle should be buck mode or boost mode. And then it does that cycle. That one switching cycle. Then it does a forensic analysis how that went, makes a decision about the next cycle, and just keeps doing that over and over and over again. So that was a complicated controller, and that's implemented in LTSpice as a mixed mode simulator.
So in the physical implementation, there's not like a micro in there or anything, right? It's doing some, or is there a micro internal that you're simulating?
I don't know if I would call it a micro in the sense that of having separate object code. And, as something, I don't think I would call it a microcontroller in the sense of having, code, data, and an ALU.
Right. Maybe a state machine, though, like state machine and some
logic.
State.
Oh, boy. It's got state machines, and it's got enough state machines to sink a battleship.
Okay.
It's
right.
It's many thousands of gates. I'm sorry. It's
really?
Not,
oh, wow. That's crazy.
It's more than 1,000 gates. Yeah, it's more than 1,000 gates, and every single gate's doing something. Because another thing in this is that it has all of these switching in buck mode or boost mode. All of the FETs are N-channel, and so it has these floating gate drivers with bootstrapped voltages above the input voltage or above the output voltage, depending whether it's in buck mode or boost mode. In boost mode, it uses synchronous directive, so the output diode is a MOSFET, and when that output MOSFET is on, you want that gate voltage well above that output voltage. And so in these floating gate drivers, you have these boost capacitors, and these boost capacitors have to cycle sometimes. But if you're just staying cycle by cycle in buck mode, then you have this input MOSFET, and you need a voltage on it above the input voltage. Well, what the thing does is every 10th cycle, it will commutate all 4 MOSFETs to recharge the boost capacitor switches. And so it's got that logic going on, too. It's a lot of logic. It's a very complicated part,
Yeah, so how did that come down then? So did they come to you and say, well, we got to get this working, and the standard models aren't going to necessarily be able to cut it. We need to figure something else out.
The guy, it was a product. It was released as a product, and then I was dealing with and it was an important product, because that is a really useful part. We've sold a lot of those. They're used like an automotive.
Yeah.
A lot of times you need 12 volt out, and you have 12 volt in, but the input can go down to who knows what while cranking and
right, yeah.
So it's used.
Yeah, you had 4 volts on a cold day, right?
No, it's a very popular part. And again, we're going to do whatever's necessary to we'll implement in simulation anything necessary to model a part. So after the product was released, I talked to the designer. Actually, all these parts, the guy making the model, I personally made the 3780 model, but we have a group of people making models. Whoever's making the model interacts with the IC designer. Okay, and he extracts the behavior from the IC designer. Now, he may use crowbar or a bolt cutters or whatever. He extracts the information from the designer to get that. It's not pretty, but
you were talking like crowbar and cutters are like on their pinky fingers or their toes or anything like that.
To find out how this part works, And so I'd ask him how this thing works, and he'd tell me enough information, and I'd come back a week later, and I was ready to metabolize more of what he had to say. And 5 weeks later, we had a model of a 3780, and I had to write a mixed mode simulator to do it.
That is, I'm just trying to imagine how many different aspects of the business you get to see as well, because I mean, man, this has got to cut across everything, right?
You know what? Let me tell you something. Simulation is just another thing that shows it's just the gosh darndest thing what a guy will do for a buck. There's just no accounting, okay? That's all it is.
That's what it is. It's not your curiosity about the world. That's probably how I would have said it, because I think only people that are curious about how the hell all this stuff works would keep plodding away at this, because this does not seem. You said you have to convince people that this is difficult, but this is difficult, man.
I was being facetious. It was a really delightful challenge. The 3780 was a delightful challenge. It was an interesting thing. There's a 3789 also with a similar amount of stuff inside it. Actually, the 3789 is a more complicated product, but it was a little bit easier to implement because it did less forensic analysis.
That's an interesting term to me too, the forensic analysis. I mean, so when you say, you're still saying the state machine kind of thing, and
forensic analysis. Forensic means after the fact.
Yeah, right.
Okay, like if you do a forensic analysis of a cadaver is after he's died. Yeah. So a forensic analysis of a switching cycle is that after that cycle has happened, you look at it, you consider it, then you can decide what to do the next. That's I'm just using it to mean after the fact.
Right, yeah. Okay. That's very, very cool. I view a lot of these components as, high level things to me, and it's like, oh yeah, of course it should, make the output go to where I tell it to go with that simple resistor setting, right? That's the Cro-Magnon way of using a switching supply. But there's so much magic underneath and all this, there's all this other stuff going on that I'm a little spoiled. I do realize this. I did want to ask you about so I think the Berkeley, not to go back to Berkeley too much, but the Berkeley one was open source. Is that correct?
Yes.
Is LT Spice open source?
No.
Okay. So because there's all these other constructs in there, basically you guys keep it as a trade secret kind of thing.
Yeah, I just got no reason to make it open source. I mean, there's no reason for me to do it. If I did, all that would happen is, right now you have small. You have like small companies trying to make a GUI around Berkeley Spice, and they'll try to say that all Spice programs on the inside are the same. The only difference is the GUI.
Right.
Well, and they do that because they have their agenda to make people want to believe that, so they can believe that what they have is as good as something else, which probably is not true.
Right, we see that a lot with web-based tools, right? That's a big trend these days. Is they put a nice GUI on an HTML5 page or something like that, and it's using Berkeley on the back end.
Yeah, well, I just have I have no reason to make LT Spice open source.
No,
it's just, if I did, what they'd say would actually be true, and I have no reason to, after they've been. I just have no reason. I have no motivation to do it. People do what they're motivated to do, and I'm not motivated to make LT Spice open source. I do not recommend making it that way.
Right? Yeah, it's such a competitive advantage for LT, like you said at the beginning, right? I mean, you saw this as a competitive advantage. I completely agree that it's a competitive advantage because I've had situations where I went into LT Spice. I pulled up. I was in a bind, right? I went in. I used a macro model and a simulation. I tweaked some parameters. I dropped that into a design. The next day, I got it fabricated, and it worked. Right? That right there is a competitive advantage because if I do that enough times and then I'm confident enough that that's going to keep working, then why wouldn't I? I mean, like, price is no issue at that point. Then, right? I mean, like that's what it says to me at least.
Sure.
Okay, cool. Yeah, and then the real reason I was asking about the open source thing is actually because I'm doing a presentation about open source, and I had listed LT Spice at one point, but I think that I had confused the LT versus the Berkeley stuff as well, right? I mean the difference there, but I think you really enumerated that well.
The Berkeley is open source. Actually, open source is maybe when people think of open source, they think of like GNU copylefted stuff. Berkeley Spice is more free than that. Basically, you can use it however you want. You can compile it in your own code and keep it a secret. You basically just can't say that you wrote it. And then there's
right.
I don't want to interpret their licensing agreement for them, but you could read their license agreement. But it's not like GNU. You actually can compile Spice into a commercial product, and you don't have to reveal the source code you used.
So we did have one or two questions on our. I think we covered some of these questions on our subreddit. One of the questions was about the Mosfet thing that I brought up. Someone else asked about integration, and so KiCad, LT Spice, and then they were asking about KiCad. Was there ever a drive to integrate with other tools outside of it? I mean, or is it?
Oh yeah, it's no problem to integrate with KiCad. What I do is I just have my secretary redraft it,
like the schematic.
Yeah.
Yeah, there you go.
Yeah, there you go. Problem solved.
Yeah, there you go.
Have your secretary redraft and you're done.
Right. Step one, get an assistant.
Actually, though, there's one other. I'm saying this answer more for technical completion than saying something that's actually useful. The useful thing to do is to redraft it. But in fact, LT-Spice can generate net lists for CAD programs. It'll do Tango and Calais 90, EE Design. There's like 30 different formats.
Yeah, right.
But I'm telling you this for academic correctness, not actual practical utility, because the fact of the matter is that is a deep feature. Unless you make a whole bunch of symbols and footprints that'll net list against the net list that comes out of that thing, it's pretty worthless.
Right.
So I will mention it to be correct, but I will not mention it as an advice of what you ought to do and saying it's a useful thing.
Right. I'm in the same boat. I mean, I always think I keep them separate because I want a physical physical schematic that's something that's going to be on a board to be pristine, and I know that my Spice models are a mess because I'm playing around in there. I'm experimenting. I'm doing a lot of stuff like that.
Yeah, and also the whole point of being an engineer, I mean, the reason why you get paid the big bucks is you cut a big problem into a bunch of little problems. Hopefully you don't have to simulate the whole thing all at once.
Right.
So the schematic for simulation, the schematic for layout are not particularly related.
Right. I don't think I was alone, and that was a big problem that I had when I was starting out, that I did try that. I tried to do the whole model. I took the whole page, and I'm like, I'll just put everything in there. And that's definitely that's silly. And that does speak to the whole idea of using Spice as a tool for specific things that because you understand most components, and when you get to something that you don't necessarily understand, you can start to dig in and play around with those individual areas, right? I did want to ask, I know we're kind of running out of time here. I did want to ask about the different types of simulation, the convergence models, and all the other stuff. I had this in my notes from before when we were talking about it. Could you help quantify? I'm trying to find here it is, control panel. So the different types of integration method, all the other stuff. Is there any reason that people should ever mess with that kind of stuff?
There is, when you see the control panel, there should be this audio recording that plays. It says, kind finger poking, hand it in and pocket keep it, But,
okay.
Yeah, kind finger poking, okay?
Okay.
There is, now you actually, and your hint there is that all of these values are lobotomized every single time you start the program. Okay. And the reason why they're lobotomized is because I'm pretty sure that I have a better value for those things than you do.
Yeah.
Okay. Now there are exceptions, and let me go through the exceptions because that's where something's important. Okay. And you'll notice the things that are asterisk. Solver is asterisk. Okay. And you have the normal or alternate solver. Okay. Now, the difference between these two is the alternate solver uses a different sparse matrix package. It uses one we wrote at Linear Tech, and it uses a different method for eliminating unknowns, different method of pivoting the matrix, and it ends up with less round-off error. That is, it's more accurate, but it's slower. Okay, so this is what you should do, but it's slower. So what you should do is, your algorithm you should apply is that you always use the normal solver unless it doesn't work. You get some convergence error message.
Okay. This sounds familiar. Yeah.
You always use the normal solver unless it doesn't work. Then you try the alternate solver.
Okay.
If it still can't solve it with the alternate solver, you're going to have to fix your circuit. There's something very non-physical about your circuit.
Right.
Okay?
Yeah.
So that's one asterisk thing, is the solver.
So I shouldn't get 2.7 gigavolts for the output to my circuit? Is that incorrect?
Well, that sounds like you're using a Boyle model for your op amp and not a Linear Tech op amp model, but I don't want to get into that right now.
Of course.
Okay. All right, so that's one asterisk thing that can be remembered or not. Now, the other asterisk thing is TR-tol. Now, the TR-tol is it says It's a directive on how accurately you should integrate the differential equations. This is an entirely different thing than how accurately it should solve the nonlinear aspect of the circuit. See, in SPICE, there's two things going on. You have these nonlinear IV curves, and you have capacitors and inductors, so you have ordinary differential equations to integrate. They're completely different aspects of the program, and that thing says how accurately you need to integrate them. Now, in industry, TR-TAL is normally 7. Every single SPICE program in the world uses 7.
Interesting.
But I set it to 1 on the PC, and as I'm solving things basically in order of magnitude more accurately than normal. And the reason why I did that, because the SPICE program was fast enough, I could afford to do it. And if I set TR-TAL to 1, no one would ever see a simulation artifact and wonder why it was showing what it was showing. Huh. However, if you're a big boy, you might want to use a larger value for TR-TAL. Let the thing run faster, and if you see a simulation artifact, you see something you don't understand, you could try tightening TR-TAL and see if it goes away.
I gotcha. Okay, so this is the smoothing it out for, or not smoothing it out, but it's used as a directive to guess how big you can make the time step as far as how accurately, to integrate differential equations, the error goes to 0 if you take very small time steps. Right. Yeah.
And if you don't take very small time steps, you have an error. Yeah. And this is a directive that says how persnickety you should try to be on integrating those differential equations. 7 is the normal number in every SPICE program in the world, but you will occasionally see simulation artifacts. On the PC, it's set to 1. On the Mac version, I've loosened it to 2 by default. You might want to set that to 2 or 3. You get to simulate a little bit faster. You'll probably never see a simulation artifact.
So it's different Windows and Mac? That's kind of weird.
Well, the Mac is it is a little weird. When I made it 1, I just had second thoughts. I decided I made it too critical. Gotcha. So on the Mac version, I set it to 2. It's essentially the same solver.
Yeah.
I mean, It's the same solver, except the Mac version is 64-bit instead of 32-bit. So all these compilers are making X64 code instead of 32-bit code. So that was the self-authoring code is in fact doing 64-bit code too. But so there's that. But otherwise, it's essentially the same solver. And the third thing that's asterisked is whether or not you should accept the European style K for a period.
Right.
And, I don't care how you feel on that.
That's a style, right?
Yeah, it's a stylistic thing. It's not really correct to use 3K4 to mean 3.4K in circuit simulation, but enough people wanted it, and it was not destructive to the rest of the syntax that if you allow it, all you do is maybe messages that you should have gotten, and circuits, it doesn't really hurt anything to accept it.
The only other ones I've ever played with are Gmin and Abstal, but that was because it was at Keithley and we were doing super low stuff anyways, and they told me to.
Gmin. Now, if you're at Keithley, you have all those electrometer things. Yes, you may need a smaller Gmin. Yes. Yeah. What Gmin is, here's the issue. A diode, it has a low impedance if it's forward conducting, if it's forward biased, and a low impedance if it's reverse biased. Well, it turns out you can't actually express if you have one diode that's forward. The trouble is that with double precision, you can't solve a circuit with a diode. The physical system has more dynamic range required than what you have with double precision math. That's the problem.
Wow. Okay. That's crazy.
So it's unusual. You don't usually see that in simulation, but it happens in electronics because you have all these exponential curves that are more or less faithfully delivered in reality. It means that if you have two diodes in series and you reverse bias them, you can't solve for the bias point because they both look like currents. So you can't solve for the intermediate value between the two diodes, and you end up with a numerical error message instead of a solution. So what's done is every single PN junction is shorted out with something called Gmin, so that if it's reverse bias, it still has some conductivity. Now, if you don't have diodes in series, you might be able to set Gmin equal to 0 and still solve the circuit.
Right.
So you can try G-min equals 0. And for electrometer circuits, I would definitely, if you can solve it with G-min equals 0, I would do that. In fact, for electrometers, I would use the alternate solver and G-min equals 0. That would be my preferred mode of operation for doing anything with electrometers.
Usually I would just build in leakage paths with really, really high frequency or high resistance parts, just kind of try and fake around it, that kind of thing.
Yeah, build it up on Teflon standoffs and
Yep, all the fun stuff. Oh, you know all this stuff. This is so great talking to you, man. This is just like all of the secrets. That's what's crazy to me. It's like all of this stuff that's under the hood. It's just like, oh yeah, I wrote that, so no big deal, right? And yet to me, like, I feel like this has been, this is this is battle scars for me. I'm like, oh God, G-min, and it's not your fault. It's my fault for not understanding it. But yeah, that's crazy.
Yeah, G-min isn't described very well in literature. It's kind of disappointing.
But it's like any other engineering type thing. You learn it from the old guy sitting in the corner. You try and like when you go crying to I go crying to them. They say, "Oh, here's what you're doing wrong." It's pretty standard, right? It's a lot of engineering companies. Are there any? What about the hacks thing? Because I'm always curious about this too.
Okay, the hacks is okay. Now, one thing about inductors in LT Spice is that there'll be a the series. An inductor has a series resistance in LT Spice by default, unless it's coupled to another inductor. Okay. Oh. Now, the reason why it has a series of resistance, is it's a node reduction technique. If an inductor has a series resistance, I can report the solution of the integration of differential equations to the part that solves the nonlinear circuit. I can report the solution as a Norton equivalent circuit. That is, a current source in parallel with a conductivity.
Yeah.
That's how I would report the solution of the inductor. If it didn't have that ESR, I would have to use a Thevenin equivalent circuit. It would be a voltage source in series with a resistance. And if I have a voltage source in series with a resistance, I have a node in between them. And that increases the size of the matrix.
Oh man, that's crazy. That makes sense to me.
Okay, so I default to a minimum. I default that to 1 milliohm, and I do the 1 milliohm value because usually it's more accurate. Not only is it fast, it's actually more physically representative. It actually is one inductor with a half milliohm ESR, and the manufacturer wanted to complain to me about it, and I told them to, it will then specify.
Right.
What it is, and it will follow that. If you say it's equal to 0, it will use a Thevenin equivalent, no problem. Now, the other thing is that it will assume that the thing has a little bit of damping. And I forget the time constant that's used, but it's really minor. It's very, very small. It's a very small amount of damping. And usually, what it does is it prevents the Q going to infinity at very high frequencies. It makes it easier to solve. Makes it again more physically. That's just a convergence hack.
Yeah,
and it's usually more physically accurate. However, if you're not modeling an electrical circuit, a lot of times people do electrical analogies. In fact, the term analog electronics came from Philbrick doing analog computers.
Yeah.
I mean, in the old days, all electronics was analog, but there was a guy doing analog electronics. He meant to do analog computers. Anyway, if the thing you're simulating actually isn't a circuit, then that damping might not be appropriate, and you may want to turn off that damping.
So this is just a big page of corner cases that, like, again, most people won't need to do.
Yeah, most people don't need this. Yeah, most people don't need that at all.
Huh. So can I put feature requests in now since I have your ear?
You can email them to me.
Oh. Okay, fine.
I have this, I went to Staples. I have this great big red button, and across it has black letters called delete. Yep. It plugs into the USB port.
Nice. That's where all the stuff goes, all of the feature requests go?
No. Some of them get implemented right away.
Yeah. See, mine were just going to be based on my stupidity, like the error where it says you can't put in zero resistance. That's just my stupidity, right? But I want it to be like, oh, he's trying to simulate a shunt, right? And Just stupid stuff on my part.
Well,
where I always get caught
actually,
up.
now, if you put in a resistor and if you give it a value of 0 ohms, it does treat it as a shunt.
Oh, did this change recently? Maybe.
Yeah, like a few months ago.
Oh, okay. See,
Someone
look at
did
this.
make that recommendation, and I said that was right. Of course, he also worked for Linear Tech, so I did it for him,
Okay. Yeah,
But
so you
that was
get
a recommendation
extra points.
I got that recommendation last December. I was in Japan last December, and one of our Linear Tech FEs said that. They said it would help them communicate the circuit to customers better if they meant 0 ohm resistors to mean give a placeholder on a PC board.
Okay.
And so I said, and I implemented it.
Yeah, it's like a usability thing, right? Where it's like that doesn't actually affect the engine at all, but it's just a communication type of thing. So yeah, it's So I don't need to ask how big your team is, but if you get hit by a bus tomorrow, God forbid, is LT Spice doomed? Because it seems like it from my perspective right now. I can't imagine how many other people in the world know all the stuff you know.
Well, I'm sure life will go on without me.
I don't know, man. This is some crazy stuff. I mean, so yeah, it's crazy.
I mean, I certainly am the most visible person with LT Spice because I do a bunch of seminars and stuff all over, but there's other people.
Yeah. Okay. That's good enough. That's good enough. I don't want you to go anywhere. That's the main thing. Let's talk about that as the last thing. So tell me about these seminars real quick. You've been traveling the world.
Yes, I am. I'm going to 6 continents.
Wow.
I'm going this year. I'll go to Europe 3 times. I'll go to Asia 3 times. I'll go to Australia once. I'll go to South Africa in a couple of weeks, and I'll go to Brazil.
Wow.
And of course, everywhere in North America. Like I say, I was just in Cleveland, Ohio, not very long ago. Yeah, you should have come up. I will miss you. Yeah.
I know. I'm kicking myself.
If you would have come, I would have given you a bass scaler. I was giving away prizes, and the prize I was giving away was a bass scaler. So everyone in Cleveland who came to the seminar has a bass scaler from me.
Am I hearing this wrong? A bass scaler? Is that?
Yeah. Well, what if you catch a delicious bass? You going to eat the scales?
Oh, scaler. Okay,
Yeah.
right. So that makes sense. Actually, up here it would be walleye. Walleye is pretty big.
Well, the pike were running, or the perch were running while I was there.
Oh yeah, did you get out and start to get any?
That's what they told me. I started giving away bass scalers, and I started hearing,
Yeah, right. Yeah, you get you get a bunch of Midwestern engineers. You're bound to hear about fishing once or twice.
Yeah,
that's awesome. So, and these are through a distributor. Is that correct?
Yes. This year they're being done by Arrow. I'm doing 57 seminars, and they're doing a great job.
Yeah.
So I just got back from Turkey. That was a lot of fun.
Wow.
That was serious. That was a great trip.
Yeah. That's great. I mean, so I know what I am and am not allowed to ask, but I mean, the people at these seminars are what are the what's the range of users? I mean, these are probably NASA scientists and also students, or is it more varied than that?
They're not invitation only. You can find on our website how to register for one. I think they started out invitation. I don't know. And it's basically whoever wants to go to them. I don't see very many students at them, and I don't know or care why that is. Most of the people doing it are actually some type of, they're electronic engineers that design circuits. Either for instrumentation companies or, they may or may not be full-time analog engineers. I've certainly met a lot of outstanding analog engineers in my travels.
Yeah. I'm jealous. There's got to be a lot of good stories and a lot of war stories and stuff like that, and probably a lot of appreciative people too, right? I mean, basically,
I must say, I'm grateful for every international trip I've ever done. They've all been very interesting to me. Yeah. In fact, that's actually how I started doing these seminars. I used to live in Germany as a student, and I wanted to go back to Europe, but I didn't want to pay for it, and that's how these seminars tours started.
Man.
So for years, for several years, I'd spend like 15% of my time in Europe, and I never did it doing seminars, but I never did a seminar in North America. I did that for like 3 years.
Yeah.
And then I started doing them in North America. And then New Horizons wanted to organize it as a they wanted to market it as a world tour. So then I started doing promoted as one tour seminars. It would be like in North America and Asia and Europe. And then Arrow bought New Horizons, and I believe they bought it because they wanted the LT Spice World Tour.
That's all right. That's a good buy then.
Yeah, and so now as they're doing an absolute record tour, they're going to go everywhere.
See, guys, I think Mike has got it figured out here. You know, don't go on travel on your own dime. This is the way to do it. You know, first off, create a simulator that everybody loves the world round, and then find people that will send you to teach people about it. I think that's a good long game. I have to say, got it all figured out, Mike.
What it is,
yeah.
Well, I'll tell you something. I'm just. To paraphrase Christopher Walken from that cowbell skit from Saturday Night Live, okay? Yeah. I'm just an ordinary guy, I put my pants on one leg at a time like anybody else. Of course, right. While I got my pants on, I write the world's best simulators, but so there's that, but... Christopher Walken did that's a paraphrase of Christopher Walken's Saturday Night Live skit.
Oh,
that was playing on the radio about a month ago. It was playing on the radio. I had to pull over. I fell out of the car.
I know. It's more a cowbell.
Not getting enough cowbells. Was where the skit went after that, but it was really funny.
Oh, that's a good one. That and the googly eyes. I like that one too. Well, Mike, thank you so much for being on the show. Obviously, people, I will try and find a link and post it so that people can find your seminars and mob you with questions and gratefulness. But yeah, is there anywhere else online people can find you? You're not a Twitterer or anything the like?
There is a LT Spice Twitter. There is some social media on LT Spice. I'm not actually, they have a person that runs all of that. And I think for me, that's the ultimate measure of the fact that I've made it, that I have someone running social media for me.
Yeah.
But I myself can be, on the help about box of LT Spice is an email address. ltspice@linear.com. That's actually my email address. If you have my business card, that's the address on it. That's how you would reach me for questions, input, complaints, whatever about LT Spice. Wow. And the seminar series, you can find those on both Linear's and Arrow's web pages. I want to, in summing things up here, I do want to express my appreciation in LT Spice, not only to yourself, Chris, to your listeners. I mean, LT Spice is the only thing I do for a living. So, in any final analysis, your interest in LT Spice is about as close to a matter of life and death as I get to a bunch of strangers. Okay, so I do appreciate your interest in it.
His life is in our hands, folks, and I think I will personally guarantee that you are going to be doing just fine, my friend. We will be sending you on trips, hopefully as long as we can.
All right.
Cool. Well, thanks again for being on the show. We're sorry that Dave couldn't make it, but I will be rubbing this in his face that I got to talk to you and he did not.
What it is.
All right. Thanks a lot.
All right. Take care.
I talked to Mike after the show, and he said Dave's actually never allowed to use LT Spice ever again. So there's that, too.